Hello, my name is Jean Cherlinsky-Ortega, and I'm here to talk to you about how some models with millions of parameters avoid overfitting, insights on deep learning and linear regression. This is an abridged version of a talk I gave in May 2022 at the Data Science Conference. As an overview of this talk, I'll begin with what seemed like an impossible phenomenon. Deep neural nets with too many parameters were able to generalize well, meaning they had low error in test samples of data. At first, it seemed like this might be something special to neural nets, but then it was discovered to be true in linear regression too, at least in some cases. Linear regressions with too many parameters could also sometimes generalize well. Recently, there have been some papers that shed light on why and how this happens, focusing on misspecified features, and it's these papers that prompted me to create this talk. Let me begin with what was impossible. We know that having too many parameters should perform poorly. We know simple is good. But deep learning models used millions of parameters and still performed well. How is this possible? Let me go back and review why we thought simplicity was so important. Simple models with few parameters are better. That's the received wisdom. Why do we believe this? Two reasons. One was just simple is good. Occam was a philosopher, and in Occam's razor, he said plurality should not be posited without necessity. So if you have something that can be explained with three causes or with two causes, you should prefer the explanation with two causes. And that's also more understandable to humans. But more importantly, simplicity has been shown to be more accurate. Empirically, we've often observed that simpler models have higher out-of-sample accuracy than more complex models. But more intuitively, it's this U-shaped curve that we think of in simplicity. On the x-axis is the number of parameters, going from 0 to however many. On the y-axis is error, and the red line, which is a U-shaped curve, shows the test error, meaning the error on the out-of-sample data set. The optimal error, the lowest point in the curve, is not at the maximum number of parameters. It's somewhere less than that. Now, if you add the training sample or in-sample data, this dashed line does go down as number of parameters go up, but the out-of-sample error has a U-shape. So when we hear simple models with few parameters are better, we should be thinking of this red U-shaped curve. So this leads to what was impossible. Let me give a little history on this. There was a contest called ImageNet for classifying images. And in 2010, the best-in-class models of the time were getting around 25% incorrect. And these were old-school models. In 2012, though, a deep convolutional neural net, nicknamed AlexNet, achieved an error rate of 16%, a jump from 25 to 16%. It just blew everyone away, how this could be possible. This was the first beginning of people wondering what's going on with deep learning. And in deep learning, the number of parameters, p, is a lot greater than the number of examples. So in the ImageNet data set, there were 60 million parameters in AlexNet, even though there were only 14 million images, so many more parameters than examples. And it turns out that images are not a unique case, as we now know. In 2016, the game of Go had a deep neural net, AlphaGo. Well, AlphaGo is a collection of many things, including some deep neural nets, that beat the best human player, which at one point it seemed like a far-off goal. Now, I don't have the exact number of parameters, but it's a lot. And we know that 50 GPUs had to be trained for 3 weeks just to train this thing. In 2020, language models soon were taking over these deep neural nets. GPT-3 had 175 billion parameters. And likewise, it also made a huge leap in improvement in performance. So the previous runner-up had 68%. GPT-3 jumped up to 86% in this particular task, Lambda. So these deep neural nets with many parameters, too many parameters, succeeded in many domains. So people started to understand something wild was going on. As T.J. Sejnowski wrote in 2020, these empirical results should not be possible. The U-shaped curve says many parameters are bad. So it turns out in 2018, an article by Belkin et al. Showed that the U-shaped curve was actually just incomplete. The U-shaped curve is the left half of this before the dotted line. It is what is called the underparameterized regime. The dotted line shows when p, the number of parameters, exactly equals n, the number of examples. This is where you can interpolate the data perfectly. If you push beyond that, in some situations, the test error can drop back down. And this is the over-parameterized regime, many more parameters than examples, and the Belkin et al. Nicknamed this double descent because there's a descent in the under-parameterized regime, descent in the error, and there's potentially another descent in the error in the over-parameterized regime. Just to get a little clearer on what this interpolation threshold is, this is the point at which the training data can be fit perfectly. So this dashed line, the green dashed line, is showing the in-sample error, and it goes to 0 at that interpolation threshold. And visually, this orange line of the model can connect all the data points in red, which is why people didn't think you'd want to go beyond this. If you can fit the data perfectly, why keep adding more parameters? But this is basically what deep neural nets are doing, and somehow it works. How does this work? Well, TJ Sejnowski wrote also in that paper I mentioned, he speculated, something about these network models and the geometry of their high-dimensional parameter space allowed them to navigate efficiently to solutions and achieve good generalization, contrary to the failures predicted by conventional intuition. Well, if it's something special about deep neural nets, then it shouldn't happen in simple linear regression that people have been using for a century, right? It turns out it happens there too. What it does visually is it draws a line through this data. This orange line is all you do. So let's see what happens. This is an example. I explained sure how I did it, but I made some R code that reproduced exactly what people have said about linear regression. I was able to reproduce it because these papers tell me kind of, here's how you set up your data to make it happen. So I have a data set with exactly 10 observations, meaning rows in the matrix. And so there's two regimes. When the number of parameters is less than 10, it's the under-parameterized regime. And when the number of parameters is more than 10, it's the over-parameterized. So once you hit 10, the training error goes to 0. And the test error, which is the generalization, it has a little bit of a U here. You can just barely see the U-shaped curve for p less than n. It spikes up. The error spikes up at exactly p equals n, and then we can see error begins to go down as we add more parameters, and this is double descent. It won't occur in just any data set. As I said, I had to use the techniques that the papers said. So let's do some understanding to see how I generated that. So there's several papers on this, but the one I found inspiring was Dara et al. 2021. They wrote a farewell to the bias variance trade-off, an overview of the theory of over-parameterized machine learning. So it was an overview, but they did spend a lot of the paper focusing on linear regression. And what they found is that when p was greater than n, there was a rich variety of generalization behaviors. It's not always double descent. It's not always just the U-shaped curve that keeps going up. There's a variety of things there, but they focused on what would result in double descent. And here are, in section 3.3.3, they outlined the necessary and sufficient conditions. So the first two conditions are a low dimensional signal structure in the data and a low effective dimension in the data. Now, a low effective dimension is more familiar to most people because it means a few large eigenvectors. The low signal structure is referring to denoised data. And just to give a quick idea, here are some diagrams showing the differences. The interesting one is the middle one, B, where the intrinsic dimension, the signal structure, is still 2 dimensions because this is on a plane. But because it's an asymmetric scatter, not symmetric, there's going to be one larger eigenvector than the other, so the effective dimension will be between 1 and 2. So at any rate, it's necessary for the large multi-parameter data set to have a core signal structure and effective dimension that are just a few, and furthermore, they should be aligned. The highest signal data dimensions must be aligned with the highest effective dimensions. So there should be a core signal in that data that, in a sense, is helping explain it. Now I'm going to spend most of this discussion on number 4, condition 4, an abundance of low signal but non-zero features in the model. Let's talk a bit about what that might mean. I suggested 2 different data sets for the task of predicting university entrance exam scores. In the scores data set, you have exam scores from prior exams, not the university entrance exam, but other ones that we know are related to the entrance exams. So, for example, a math exam score, a language exam score, and a logic exam score. These are going to be great predictors for entrance exam scores. In contrast, we could have another data set. I'll call it the social media data set. For these students, we have nothing with exam scores. All we have is this incidentally generated data. We have their Twitter posts, their likes, the location of the Twitter posts, Instagram posts, etc. You might say the person who has content about history and posts in the library might get a higher exam. But it's a very loose connection. These are the low signal features, an abundance of low signal features, and they're misspecified for this data set. In contrast, the scores data set with the other exam scores is well specified. So this is the example of the difference. We'd expect that the double descent would occur in the social media data set, not in the scores data set. But I can't prove this. I can't run my own regressions because I don't have either of these data sets. So instead, I constructed my own set of two data sets to do this for predicting miles per gallons of cars, starting with a well-specified data set, which is available in the R language. It's called MT cars for Motor Trend Cars of the Year. And for each car, it included a number of 10 parameters. So how did I create a new data set that satisfied those 4 conditions so I could see double descent? Well, I added 20 more predictors, and they were random normal distributions with a mean of 0 and a standard deviation of 1. And then what happens is when I ran my simulation, if, for example, those are the misspecified features, if I wanted to have 3 parameters, I would randomly pick 3 from the well-specified data set. So in this case, I picked displacement, transition type, and carburetors. And I would randomly pick 3 from what I call the empty cars of the random, the poorly specified data set. This might hit rear axle ratio, then parameter 11, which is random normal, and parameter 30, which are random normal. Now, clearly, 11 and 30 are not going to be very useful. So you're only getting one useful parameter in this. But in any case, you can still fit a regression model to the data and measure the test error. So that's what I'm going to use to generate these plots. So here's a plot comparing the mean test error for the well-specified data set in blue and the misspecified data set having this other shape in red, empty cars with random. So what you can notice here is if you have well-specified features, the lowest error is with a few number of parameters. It's not using all 10 parameters that we had. Looks like it's about 3 there, or 4. But at any rate, it's somewhere lower. This is the U-shaped curve we talked about. But if you have misspecified features, the red line, the lowest error is with lots of features. It's with all 30. And then here comes the other part. The error at all 30 from this misspecified features is not better than what we had in the well-specified features. In this case, it's still better to use the original data set if you have it without the noise in it. Now, interestingly, that's not always true, but that's a whole nother can of worms I won't go into here. All right, if that was too much theory for you, I'm going to just tell you what to do. Basically, it depends which type of data set you have. If you have well-specified features, select a small model with few parameters. Simplicity rules. If you have low signal features, collect as many of them as you can. If you already got the Twitter post and Instagram post, see if you can get the Facebook post too, or some cell phone signal data. Lots of parameters will help. Strive to get to that double descent point. Get enough that you get that second descent. Simple models with few parameters are better when you have well-specified features. That's how we update that wisdom. There's also another piece of wisdom. More features are better when you have poorly specified features for a good core signal. Of course, there's all kinds of other data sets than just those 2 archetypes I set up, and they have a variety of generalization behaviors. That's what was mentioned in the Dar et al. Paper. This is a cool area for future research. That's the core part of the talk, but I did want to offer 2 reflections real quick. One is successful overparameterization is related to some things we've seen before, such as ensemble models. With ensembles, you typically do better with the more models you add. Same with boosting and bagging. The other thing I thought about is, why did we only discover double descent now? We have known about linear regression for centuries. Well, there's different data sets now. Now we have an abundance of these low signal data sets collected incidentally from this digitized world. If you want to keep learning, here's the core bibliography. You can take a screenshot. And here's the blog post and a link to the code.